We continue from where we ended last week. So, energy within the atom. So, we said last week to say all atoms possess energy. And why this is so, it's because you see, like we said, the nucleus is going to be central, then electrons are going to be where? Are going to be around, okay? So, then what's going to happen, like I said, is that the nucleus is positive, the electrons are negatively charged, and that's why because of those attraction forces which occur between the electrons and the nucleus, that's why you will see that the electrons don't move far away from where uh, don't go far away from the what, from the nucleus, so they'll always be near the what, they'll always be near the, of course there's going to be some distance from the what, there's going to be some distance from the new between the nucleus and the electrons, but then they won't be, the electrons won't go far away from the nucleus. Why? Because of these attraction forces. And so of course this is energy, right? This is energy that is being used. And then one thing is that you will realize that also the electrons are not put into the nucleus. So what does this mean? It means that in as much as these electrons are being put towards the nucleus, they don't go into the nucleus. Why? Because they're also repulsing force, or rather, these electrons actually have energy to what, uh, to keep the electrons wanting to go away from the nucleus. So it's as though that attractive force is trying to set an equilibrium between the electrons which are trying to be pulled away and the electrons are being, or rather, the electrons want to go away from the nucleus, and the electrons want to be, and the attractive forces rather, which are attracting these electrons. So then what this means is that there is energy needed to do this. Okay, this attractive force that is countering the repulsive force is very very important. Okay, and the energy needed to do this is similar to the energy it takes to hold an apple in your hand when gravity is pulling it towards the ground. So here's the thing, there is, when you've got an apple in your hand, we know that gravity is there. And what is gravity doing? Gravity is trying to pull this apple where towards the ground to ensure that it reaches downwards. Because remember, as we talk about gravitational potential energy, we know that so long as something is raised above the ground, it's going to have gravitational potential energy. So that apple, when you hold it in your hand, it's going to have one, it's going to have gravitational potential energy. And so the same thing as the apple in your hand and the electrons moving around the nucleus, both possess the what? Both possess energy. And what would happen is that if you were to drop this apple on your foot, perhaps you may then be hurt because that potential energy would have done work on your foot. Okay, so electrons also have energy, okay, due to their motion or kinetic energy. So that apple is just simply in your hand, so it's been raised, isn't it? So because it's having energy because of its position, it has what? Potential energy. But the electrons are not just held somewhere. No, no, no. These are continuously moving. And we know that the energy of motion is what? The energy of motion is kinetic energy. Okay? So the energy of motion is kinetic energy. So these electrons have kinetic energy. That's why you will remember, and maybe when we review the the atomic structure in chemistry, you may remember us talking about the what's this, the energy of electrons. Huh? You remember those photons and everything, and I remember us talking about what? Talking about the energy that electrons have. So electrons have got energy. Okay, they have energy. So that's something that's very very important to take note of. So since the energy of an electron since the amount of energy an electron possesses is related to its distance from the nucleus, therefore Electrons that are the same distance from the nucleus have the same energy. So what is this saying? What this simply saying is that, remember, we've talked about shells, we've talked about orbitals. So these electrons which are in that orbital, they are going to have the what? They are going to have the same energy. Why is it so? Because the amount of energy is related to the what? To the distance of the what? Of the electrons from the nucleus. So that's an important point to take note of. Having said that, so then now here's the interesting part. The electron that is so the further an electron is from the nucleus, the more energetic it is. Why is it energetic? Because it has so much energy, okay, that it's able to repel the what? The attractive force of the what? Of the nucleus. So meaning this is an electron which has so much energy that it's being put by the electron, or sorry, it's being put by the nucleus, and what's happening? It's still maintaining its position. But of course, being more scientific, we discussed in chemistry when we were looking at atomic structure, to say it's actually those things to do with the Bohr model and things like that, right? Where we're able to look at those quantum numbers, and then we're able to appreciate where this energy comes from. But because this is biology, that thought can be helpful. So now, having talked about that, now we can proceed to talk about chemical bonds. So remember, we talked about how atoms can form a molecule. So when two atoms come together, when atoms come together, they can form a molecule, they can form a compound, right? So what happens then is that the atoms in a molecule are going to be held together by what? By what we call chemical bonds. So they are going to be held together by what we call chemical bonds. So what's going to happen is, yeah, so about chemical. Then the making and breaking of chemical bonds involves energy, and we discussed in chemistry during bonding to say making a bond releases energy, isn't it? Breaking a bond uh, takes up energy. Think of it, when you are trying to separate, let's talk of electrolysis, right? So electrolysis is where you are separating the what? You are separating water into hydrogen and oxygen, and we use what? We use electricity. So that just shows that there is energy that has to be put into what? That has to be put, that has to be added, that has to be used. So then what that entails is that energy is being used up. Okay, so energy is being used up, and that's something that is very important. So there is energy that is being what? There is energy that is being used up. So that's something that's very important. So bond making generally produces energy. Bond breaking generally involves energy consumption. Okay, so these chemical bonds come in three types. So of course, the main ones: ionic, covalent, and hydrogen bonds. So isolated atoms are usually unstable because the outer electron shell is not full. So basically, what they are talking about in chemistry, you learn about what we call the octet rule and the duet rule. So what this basically means is that for atoms such as hydrogen and helium, for them to be stable, the outer electron shell needs how many electrons? Two electrons. So they are called the what? They are called, they obey the duet rule. So that's why hydrogen, when it reacts, it only requires how many electrons? In its outer shell, only two. Okay, but then the other atoms, except these two that I've talked about, for them, they obey the octet rule. So what the octet rule basically says is that these atoms are going to be very stable when their outer electrons are what? Have eight electrons in them. And so they are going to have a what? To have a stable state. So what this entails is that there are certain atoms which are good at losing electrons, and others are good at gaining electrons. So what happens is, when you've got one atom which is good at losing electrons, and the other which is good at gaining electrons, what you're going to have is that the one that loves losing electrons is going to lose the electrons. The one that loves gaining electrons will gain those electrons. So what's going to happen? Here is what we are seeing. So sodium really loves to what? To lose electrons. So you see there, it has lost an electron to become what? To become sodium ion. And remember, we said last week to say, in a neutral atom, what you are having that the number of protons is equal to the number of electrons. But we see that this has lost what? One electron. This means that the protons are more than the electrons, right? And you can see there that the protons in the sodium ion are 11, but the electrons are what? Are 10. So it simply says you've got 11 positives and 10 negatives. So the overall is going to be what? A positive, isn't it? So that's how you can look at it. Huh? So now you see there, when you look at the outer ring for the sodium atom on the far left, you see that it has what? One electron. So it's not satisfied. Because remember, this one follows the what? Follows the octet rule. So it needs to have, of course, we remember that octet from octagon means 8. So you see, so that sodium needs 8 electrons in its outermost shell for it to be stable. And how does it fulfill? So you're also looking about which one is easier. Which one is easier, to lose just that one single electron or for sodium to gain 7 electrons? I'm sure you're thinking it's better to what? It's better to lose one electron than having to find ways of gaining what? Ways of gaining 7 electrons. Think of this. You're asked to say, okay, give us, maybe let's say, okay, you've been tasked to say, okay, get rid of this coin that you have, or keep this coin and go and find 7 more coins. Which one will be easier? Simply give away that one, and then you go your own way, isn't it? So that, and then more so for these atoms, they are going to be even much more stable. So that's something that's important to take note of. Okay, so we've talked about that. Yeah, so that's what we are going to see. So now, if yeah, so if the molecule that is to be formed, it's between an element that loves to lose electrons and an element that loves to gain electrons. What's going to happen is that the one that loves to lose electrons will lose electrons, and the one that loves to gain electrons want to gain that electron. And this is why you have to be careful, because it means that how many electrons are going to be lost, or how many sodium atoms are going to be required to react, is dependent on what? Is dependent on the other atom which it's reacting with. So in this example, we've got chlorine. So when we look at chlorine there, you see that the outermost shell has got how many electrons? Has got 7 outer electrons. And so which one is easier for it? Because remember, it only needs one to be stable, or it can lose 7 to be stable. So which one is better? Simply to gain one, isn't it? So it's going to gain 1 electron. And remember, in a neutral atom, the number of protons and number of electrons are equal. And in the ion, the number of protons is so the number of protons is going to be less than the number of electrons. So there we've got the negative charge, because now the negatives are greater than by 1, isn't it? So that's an important point that you would like to take note of. So now, what would happen if the substance that we had, or the other atom that we had, instead of chlorine, we had, let's say, something such as so imagine if we had maybe something like oxygen, right? So oxygen has got six electrons in the outermost shell. So how many does it need for it to be stable? It needs two. It needs to gain 2 electrons. So meaning, if sodium is reacting with oxygen, it means that for sodium oxide to form, and you see the symbol, or rather the chemical formula is what? Is Na2O. What does that mean? Na2, it means that you need 2 sodium atoms Okay, you need two sodium atoms to release how many? One electron each, so to make two electrons, and then you only need one oxygen atom to be able to gain those two electrons to form one more of what? Sodium oxide, right? Exactly. So that's how all. So that's why you. So you can see that just from the understanding of this, you can be able to understand even the chemical formula, right? Great. So that's pretty much about it. So now we've already talked about an ion, but an ion is simply an atom or group of atoms that carries an electric charge. So a group of atoms that carries a charge, we call that a radical. Huh? So for instance, you've got things like sulfate, you've got things like phosphate, you've got things like chlorate. So when you've got a group of atoms which has got an electric charge, you call it a radical, isn't it? Yeah, but an ion is an atom or group of atoms that carries an electric charge. Great. So electric charges result from the transfer of electrons between atoms. So I've already explained that. Okay, great. So I've explained all these things. So example of losing electrons. So I've already talked about sodium and why it's becoming positive. I've talked about chlorine and why it's becoming a chloride ion. So now there you see. So now I've got the so you see that picture when you go to your right, you see that there's the sodium that's positive and the chloride ion which is negative, right? So they are going to be what opposite side, opposite attract, isn't it? So what's going to happen there is you're going to have that attraction. So you're going to have the sodium chloride molecule, which is NaCl. So you see the ratio of those atoms is 1 to 1 because one electron lost is sufficient for the chlorine to gain to become a chloride. Huh? But of course, we saw that it's a different scenario when we are looking at something like oxygen and sodium. But again, when you've got something like magnesium oxide, remember, magnesium will lose two electrons for one more. So meaning when it loses those two electrons, when it's reacting with oxygen, because it has released those two electrons, meaning the oxygen is going to gain two electrons, isn't it? So you see that one more of what of magnesium is sufficient, for that transfer between the oxygen and the what and the magnesium. Huh? So that's where you see that the chemical formula for magnesium oxide is what MgO. You see, so there is no two anywhere because it's one more or rather one magnesium atom with one oxygen atom to form magnesium oxide. Of course, with the magnesium losing two electrons and oxygen gaining those two electrons. Great. So that's about it. So now an ionic bond, like in the case of magnesium oxide, sodium chloride, sodium oxide, an ionic bond is formed when an atom of sodium, so we are talking about sodium chloride, when an atom of sodium transfers its outer shell electron to an atom of chlorine. Having given up an electron, sodium becomes positively charged. Why? Because there are now less electrons than protons, isn't it? Then, having received an electron, chlorine becomes negatively charged. Why? Because there are more electrons as compared to the protons, right? So the two ions have opposite charges, so they attract one another. They attract each other. The force of attraction between them is strong, and it is this that we call an ionic bond. So because sodium chloride is made up of ions, that's why we call it a what? An ionic compound. So that's pretty much about ionic an ionic bond or ionic bonding, right? So we now talk about covalent bonds. So remember, I said for the ionic bonds, you've got an atom which loves to lose electrons and another that loves to gain. Okay, so you can think of it as friends that one loves giving gifts and the one loves receiving. So, but now for covalent bonding, what you're going to have is both electrons don't easily lose sorry, both atoms. Okay, so the atoms that are reacting, both of them don't like what? Both of them don't like gaining. Okay, so they don't like, sorry, both of them don't like losing electrons. So because they don't like losing electrons, what's going to happen is they have to agree on something. Okay, in short, they have to make compromises, isn't it? So they have to compromise and say, since we since we both don't like losing electrons, we both don't like losing electrons. So what are we going to do? We are going to share them. Or you can think of it, you are trying to buy something good with someone, and then you say, you know what, let's just share the costs. And so you share the costs exactly. So that's where the covalent bonds come from. It's as a result of two atoms which both of them don't like giving or don't like losing electrons, but they love gaining electrons. So because none of them is willing to give, so what's going to happen is they will share. They will say, okay, you know what, we both don't like to give, so let's just share. And that's what's happening in that example. So you see that hydrogen there. So you see those two hydrogen atoms. You see that the electrons are being shared there, and you see, so those electrons are being shared there. And we talked about hydrogen obeys which rule? The Duet rule, right? So meaning that so long as each hydrogen atom is surrounded by two electrons, it's satisfied. So when you look at the hydrogen molecule, you see that when you take one hydrogen, you see that it has got two electrons around it, and also the same thing for the other hydrogen. So means that for hydrogen, the Duet rule has been what? Has been fulfilled. And once it has been fulfilled, hydrogen atoms are satisfied. Okay? So hydrogen atoms are satisfied. So that's basically what covalent bonds is. It's simply about making compromises and say let's share electrons. So another good example that we will look at is methane. That's how you call it in organic chemistry, but in organic chemistry, you call it what? Carbon tetrahydride, isn't it? So again, when you look at carbon and hydrogen, both of them are not good at losing electrons. Okay, they are not good at giving electrons. So what happens? They'll agree on a compromise to say, you know what, we we both don't like to give, so let's just share. So you see, that's what's going to happen. So you always want to check whether the rules for the particular atom have been fulfilled. So we know that hydrogen and helium, they go by the what? They go by the Duet rule. So you see that all the hydrogen atoms are surrounded by what? By two electrons. You see that two electrons are being shared. So meaning the hydrogens are comfortable. So now you have to look now for carbon. Is the carbon atom surrounded by eight electrons? Being shared. So you see here, 2, 4, 6, 8, isn't it? Yeah. So you see, the carbon is happy, the hydrogens are happy, and so yeah, that's convalent. That's convalent bonding. So that's what convalent bonding is all about. It's just sharing electrons, and so there you have it. So now we're now going to talk about hydrogen, because you may know that hydrogen is very important, of course, being a constituent of water. So that's an important thing. So hydrogen, as we may know, a hydrogen atom has only one electron. Its shell can hold two electrons. So we've talked about it. So the fact that it has got one electron, meaning that it's not satisfied, it needs another one. It needs another electron, right? So these are basically what we've been talking about. Okay, great. So now, okay, so now would also want to talk about what we call double or triple bonds, etc. So uh Okay, so just before I can talk about that, let's just look at so you see those drawings, they're showing how the molecule of water is, huh? Yeah, so you see you've got two hydrogen atoms there. And why do you need two hydrogen atoms? Because for the oxygen to be satisfied, it needs how many electrons? Two electrons. And each hydrogen is only sharing how many? One each. Yeah? So meaning that to fulfill that deficit, to fulfill that gap, to fill that gap, you need what? You need two electrons. And because each hydrogen is only able to give one electron, so then you need two atoms of what? Of hydrogen. So that's what we are having there. Huh? So they've shared their electrons, and then you see oxygen now has got 8 electrons in the outermost shell, and hydrogen has got two, so everyone is happy. I'm sure you can see those signs, which are, they are like sigma delta, sorry, they are like delta plus, delta minus. So those symbols, what they are just showing is that those are slight charges, and we'll talk about it when we talk about electronegativity. But what I would just like to say, what is electronegativity? Don't worry, but I'll talk more about it. But electronegativity simply talks about how much a particular atom loves to draw electrons to itself in a compound. So this is uh, the value or the amount or the ability of an atom to draw electrons to itself in a compound or in a molecule. So when we say oxygen has got a high electronegativity, what are we talking about? We are saying that oxygen loves to draw electrons to itself. And when we say that hydrogen has got a low electronegativity, what does it mean? It means that hydrogen isn't really in the business of wanting to draw so many electrons to itself. So now, what are the implications? Let me just talk about it briefly, but we'll dive into it more when we start talking about why water is polar. So what happens is that when that water molecule is formed, the electrons are not going to be shared equally. You saw that for the others that we are talking about, we didn't have these slight charges because the electronegativities of the involved atoms were not very different from one another. And how you can picture this is, imagine if you and a preschool going child were pulling on something, right? Like you're trying to grab something. Let's say you've got a door, or maybe you can say you're trying to grab something from this child, from this preschool going child, and then you're trying to pull it. You realize that it's going to be easy for you to pull it out of the child's hands, isn't it? And the reason is that you are stronger, you are older. But someone of your age, it may be tricky, and sometimes you may even lose what you are trying to pull from them. So the point, that's what electronegativity is just now what they are pulling, what these atoms are pulling out are electrons. So in the case of hydrogen, it's got a low electronegativity value, whereas oxygen has got a high electronegativity value. So what does that mean? It simply means that when they shared electrons, hydrogen is going to pull the sorry, oxygen. So oxygen is going to pull the electron very, very much to itself, so much that it's going to become slightly negative. That's why you are seeing the negative, the slightly negative charges there being on oxygen. And you see that on the hydrogen, you've got what? You've got the slightly what? Positive. Why is the slight positive there? Because electrons are not equally shared, and so the hydrogen atoms are slightly what? Deficient of what? Or rather they are slightly lacking. Okay, so the electrons have been pulled quite further away from the center, isn't it? So they are having some form of positivity in their value, or in their charge. Yeah, in their charge is better. So now, of course, as these atoms share electrons, they are what we call double or triple bonds. So what this simply happens is, remember, when a pair of electrons is shared, you've got a single bond. When two pairs of electrons are shared, you've got a double bond. When three pairs of electrons are shared, you've got what? A triple bond. So you always look at a pair. So if three pairs of electrons have been shared, which is about how many electrons? Six electrons. So then you've got a triple bond. If you've got two pairs of electrons shared, or four electrons shared, you're talking about what? A double bond. Okay. So now, uh, that's talking about hydrogen bonding, and yeah, but we'll dive into that a little in a short while. So we're now talking about the molecule water. So like we've already seen, uh, a molecule of water consists of two hydrogen atoms and one oxygen atom, and each oxygen atom has six. Anyway, these are things that I've already talked about, where I said each oxygen atom has got six electrons in its outermost shell. So for it to be stable, it needs two electrons, and each hydrogen atom has got one electron. So meaning, how many atoms of hydrogen are going to fulfill the gap that oxygen is having? You need two atoms, right? So then what's going to happen is that one atom of oxygen is going to react with two atoms of what? Of hydrogen to form water. Okay, so that's something that's important. And then I talked about electronegativity there, and I explained. And so because of this electronegativity, that's why you see that on the part of the water, so you see the water, you see that oxygen is slightly negative, then the hydrogens are slightly positive. And so what does this tell? This then makes water molecule to be what? To be polar. Why is it polar? Because um what's happening is that the oxygen is slightly negatively charged and the hydrogen is slightly positively charged. So it's as though the charges have been separated. So that's why water, we say water is polar. So that's an important point to take note of. So when two water molecules are in close contact, these opposing charges, so which opposing charges? The slightly negative charge on the oxygen, and the slightly positive charge on the hydrogen atoms, they are able to interact when water molecules are in close contact. And what are we going to have? We have what we call the hydrogen bond. So what are we going to do? Let's now look at this diagram. This is where the money really is now. So you see how, okay, so just watch out for my pointer, so you can see this pointer. So how these hydrogen bonds occur is that it's always a hydrogen being linked to a what? To a very electronegative what? Atom. So why am I stressing that? Because it's not only in water that you get hydrogen bonds. You can get hydrogen bonds in many other what can I say? Molecules. So long as the hydrogen in that molecule is slightly positively charged, and then those molecules or those compounds have got a very, very electronegative what? Electronegative atom, which is slightly negative. So it's the charges which are interacting, okay? So of course they are slightly positive, slightly negative, but when they are in close contact, they'll be able to form a bond, and it's what you call the hydrogen bond. And this has so many implications for water, because it's why water has got all these wonderful, wonderful properties. Yeah. So that's pretty much about it. So Therefore, attraction is between a partially positively charged hydrogen in a molecule and some negatively charged oxygen atom in another molecule. So why am I stressing this? Because there are times where Dr. Shatta will draw that, and then would draw something else which it will have uh, like you've seen this hydrogen, but he will also connect it to a hydrogen, not to an oxygen. And someone will just rush and say, "Oh, I got the correct answer." So whenever they bring you something like this, check all the bonds. Don't get tired by just looking at one bond, because they can just change something on where they are linking those hydrogen bonds. So you always want to check that it's from a hydrogen. Hydrogen atom, which is slightly positively charged, to what's this? To the electronegative what? Oxygen. Of course, it cannot only be oxygen, depending on other substances which have what? Which can have hydrogen bonds. So that's an important point to take note of. You dive more into this in chemistry, but for biology, this is the best you can know about this. So I've already talked about electronegativity. So that's what they are talking about there. Okay, yeah. So uh, so that's the electronegativity there. So you see that oxygen is more electronegative than nitrogen. Nitrogen more electronegative than sulfur. Then sulfur and carbon the same. Okay. So that's an important point to what to take note of. So you see that hydrogen amongst the most common elements that we have in our body, it's the least electronegative, right? Okay, so that's pretty much about it. So now, what is really interesting about the hydrogen bond? The hydrogen bonds on their own, they are very weak bonds. So these are very, very weak bonds, but it's because they occur in large numbers. You can imagine each water molecule is going to have four hydrogen bonds around it. And also, that's a question that comes usually in your tests, exams, to say how many water molecules can surround a single water molecule. So you are basically looking at that structure that we are looking at. Yeah, like how many water molecules are surrounding that central water molecule? Four, huh? So that's an important point to take note of. They love that question. Okay, so we've done that, we've done that, we've done that. Yeah. So so on their own, hydrogen bonds are weak, but because they occur in large numbers, that's why they are able to maintain the shape. They are able to hold strong, and that's why they're able to give water so many amazing, interesting properties. So this is, it's interesting to note that it's the hydrogen bonds that join the two strands of DNA. Okay, that join the bases in DNA. I think that's interesting. Okay, so we've talked about the hydrogen bonds in water. Now you see on the right, and that's what I was saying, that hydrogen bonds can occur, but can occur between different molecules, right? But of course, our focus was on water. But so you see on your right, what you are seeing there is what is the hydrogen, which is slightly positively charged, going to where? To the negatively charged with what? Uh, Nitrogen, you see? And nitrogen is a very electronegative what? Electronegative molecule. It's just less electronegative than oxygen, but more electronegative than the rest. Obviously, sodium, carbon, phosphorus, hydrogen. Huh? So meaning it's going to be slightly negatively charged when it's bound uh, with um, hydrogen, like in ammonia. So the hydrogens are going to have slightly positively charged, and the nitrogen is going to have a slightly negative charge, and so a hydrogen bond can occur. Okay, between the hydrogen in water and the nitrogen in ammonia. Of course, it could also occur probably between the positively charged hydrogen in ammonia to the negatively charged oxygen in water. So again, that's important. So don't just be restricted to water. Don't just be restricted to water. Don't just be restricted to water. So a hydrogen bond can also form between a nitrogen atom in a molecule and a hydrogen atom in another molecule. So it's not always formed between two, uh, similar molecules. And that's why you find that certain things are able to dissolve in one another. Hydrogen bonds may play a role, isn't it? Okay, so now talk about water. So all this building up is just to build up on the concept of water. Then we now look at the interesting features of water that really makes it this they call it very important molecule with regards to life, isn't it? So water is a solvent of life. Every cell is 70% water, and almost all the chemical reactions in a cell or within a cell are happening in aqueous solution. So in short, usually things occur in solution. And of course, the solution, the aqueous solution, water is what is a solvent. And so that's why you say life may have evolved in water. So really, when you look at it, is water is really at the core of life. Huh? It's at the core of life. So we've already talked about how water is formed. So let's now talk about the characteristics of water, and then that's going to give us a better idea about water, and I feel it's going to help us appreciate uh, this wonderful molecule. So first things first, states of water. So water has got three states, right? And these states are going to be dependent on what? Are going to be dependent on the temperature. So if you get water and then you reduce the surrounding temperature, or maybe you put it in the freezer below freezing, water is going to be what? To be solid. It's going to be an ice. Huh? Then between the freezing point and the boiling point, so between 0 degrees Celsius and 100 degrees Celsius, water there is going to be a liquid. And above 100 degrees Celsius, above the boiling point, water is going to be a gas. So the interesting words that are used to, to describe the changes in the states of matter, or rather in the states of water, okay? In the states of water. So from solid to liquid, melting, liquid to solid, freezing, liquid to gas, evaporation, gas to liquid, condensation. And the important, okay, everything is important, but the ones which most people are most likely to forget is from gas to solid, which is frost, okay? And then from solid to gas, sublimation. So those last two, ensure that you're comfortable with them. Okay, so that's the first part. The second point is water sticks together. So why is this important principle interesting? Here is the catch. Water is a neutral molecule. Why is it neutral? It's because you remember something can only be charged if the net charges are not zero. But you may be like, hey, but why is it that there were positives and negatives? But those balance themselves out, and so we could say they cancel in some sort. Okay, but then so that's what's happening, right? But inside that water or the water molecule, yes, outside it's neutral, right? Because those charges we've talked about, they balance themselves out. But what happens is that uh, the nucleus of the oxygen atom will pull electrons where away from the nucleus of what. So remember, this is just talking about electronegativity, right? To say oxygen has got a higher electronegativity than hydrogen, so the electrons are going to be pulled from where they are being shared, and they will be closer to the what, to the oxygen atom, and therefore it's going to be slightly negatively charged, and the hydrogen is going to be slightly positively charged, and what you're going to have is a polar molecule. So because of that polarity, because of those slightly positive, slightly negative charges, they allow for the formation of the hydrogen bonds. And so we said, even though these hydrogen bonds are weak on their own, but together they are very, very important. Again, the question that they would love is how many water molecules can surround the maximum number of water molecules that can surround a water molecule by hydrogen bonding. It's 4. Then water as a solvent. So water is a very, very interesting solvent because you will realize that usually certain substances, especially solvents, they tend to be very hard lined. So by hard lined, I mean if something is non-polar, it will be very difficult for it to dissolve something polar. But water is able to dissolve a wide variety of substances. But that's not to say that there are certain things that don't dissolve in water. They are there, things that don't dissolve in water. But in comparison to the other thing, to the other solvents, we would say water is a very powerful solvent. Okay, so when a chemical dissolves in water, it is free to move about and to react with other chemicals. Okay, because water has slightly positive and negative parts, it will attract other charged particles such as ions and other polar molecules. So how then they would ask this question to you is they would give you a certain, there's a common drawing. Okay, anyway, let me explain it, then I will see how to do it. So for example, in a solution that contains cations, so we know cations are what? These are positively charged ions, isn't it? So in a solution where you've got cations, so cations are what? Cations are are positively charged ions. So what's going to happen is that when you put those things like sodium, potassium, they are going. So when you put sodium ions or potassium ions in water, what's going to happen is that they are going to be surrounded by water. Now, how is the water molecule going to orient itself? What's going to happen is, remember, the hydrogens on the water are slightly positive, so they can't interact with something positive. So the part of water which is going to attach, to be in close proximity, or rather which is going to which going to get attracted to the positive cations, or rather to the positive cations, because we know that cations are positive ions. So the part of water which is going to be attracted to the what, to these positive ions such as sodium ions, potassium ions, is going to be the oxygen part. Why is the oxygen part going to be attracted to these positive ions? Because it is the oxygen atom which is going to have a what, a slightly negative charge. So that's why the positive and the negative is going to be very, very important in this regard. So that's something that's very important. So how Dr. Shatta will bring the question is he'll draw some things where there'll be a cation, and then he will draw the water molecules where it's the hydrogens which are close to the cations. That's wrong, because the hydrogen atoms are what? The hydrogen atoms are slightly positive. Positive and positive will repel. And then there will be one where he will draw correctly, and the other one he will mix them. So be wary of those. Be wary of those. So the key thing is, if it's the positive ion, ensure that when you check all the surrounding water molecules, it is the oxygen part which is being attracted to that cation. Then if you then get an anion, so an anion, this is a negatively charged ion. So for instance, chloride. So what's going to happen again? The opposite is true. The What you're going to have is the hydrogen, in this case, the hydrogen atoms of water, since they're the ones which are slightly uh, what can I say, slightly positive. So they are ones which are going to get attracted to the what? Which are going to get attracted to the anion. Okay. So, however, so that's about the ions. Huh? In contrast, non-polar molecules such as lipids will not dissolve in water. Will not dissolve in water. But again, when you look at polar molecules, will dissolve in water. For instance, let's talk of glucose, for instance, sucrose, for instance, those are able to dissolve in water. So you see, ions will dissolve in water, polar molecules will dissolve in water, and it's only the non-polar molecules. So if you put the ratios, it's like water dissolves two-thirds of all substances that we have, isn't it? At least you can think of it, because yeah, the ions and the polar molecules. But the point to take home is that water is going to dissolve a lot of substances. Okay, so the hydrophobic water hating property of lipids is very important in making the stability in cell membranes. So when we talk about lipids, that's why now we see how the fact that lipids don't interact good with water, or the fact that lipids are hydrophobic. Phobic means hate. Huh? Okay, so hydro, it's water, so water hating. So it's because of that the cell membrane is a bilayer, because all that is happening is the lipids are trying to protect themselves from the water molecules. But when we talk about lipids, we'll go into detail on that. Then molecules which dissolve in water are called hydrophilic. That is to say, they are water loving. So that's about it. So tomorrow we continue and talk about the the high melting and boiling point of what, of water. And of course, remember, as you may have already seen, all these things are coming to happen all because of what, all because of the hydrogen bonds which are in the water, which are occurring between the water molecules. So with what we've talked about, are there any